Okay, good morning again, everyone. And today we are going to sort of continue on what Santanu has taught you guys on delays. So we'll do some switching analysis. And mostly what we'll be talking is, I'll just introduce you to the delays, the formulation of delays in CMOS gates. And then we're specifically going to look at how to optimize the buffer. So when you have a big capacitive load and you want to drive it, how to create this buffer chain or set of buffers to drive it with a minimum delay for a given technology. And that will actually lead us to what we are going to introduce. We're not going to go deep into it, but just introduce the concept of what's called logical effort. And it's essentially a process of optimizing delays in arbitrary paths containing arbitrary gates, right? And that's what you'll be experiencing as digital designers. Um, Specifically people who are going to do on the physical design side, 90% of your job is going to be doing these delay optimizations, basically. So you're going to get all these um, reports. Like for example, if you're a STA designer, you're going to get all reports, and typically what you'll be dealing with is what's called critical path, right? So you have a clock frequency, and you want to drive your circuit with the fastest clock frequency, especially when you're doing high-speed designs, right? And essentially you want to make sure all your delays, or at least from one clock edge to another clock edge, uh, all the delays involved are in that clock cycle. If you are more than that, then obviously you have a problem. And I think Puneet in his first class talked at length, um, how you have set of violations and hold violations when you have basically finite state machines, basically flops capturing, and pretty much all digital circuit is essentially dealing with that timing between a launch and a capture edge. So for example, you might get a report back saying that this is a path which is in the PD language it'll be called critical path. So critical path in the sense, this is your highest delay, and that's what is restricting your clock frequency. So for example, let's say you have a big digital circuit, and typically you get a lot of violations, but you might just get one violation saying that, by the way, you're trying to run it at 100 megahertz or 1 gigahertz. So 1 gigahertz means this is 1 picosecond, but then this critical path delay is more than that, so you cannot run it at 1 gigahertz. So obviously one way is you just slow your clock speed down, but obviously that's not what your intention is. Your intention is to run it at clock speed. So you have to figure out how to minimize this delay, right? So that's what mostly what we'll be talking about today, is how to minimize this delay for a set of inverters or a set of gates with arbitrary, I mean, a path with arbitrary gates. Okay, so for calculating delays, I mean, there are various ways you can calculate delays. Like for example, you can calculate from the switching point of one gate to the switching point of another gate, but the switching point varies a lot depending on how you have sized. Um, so that's why throughout this analysis, what we are going to do is we are going to take 50%. So from high to low or low to high, we're going to take from the transition of the 50% from the input to the 50% of the output, and we're going to call that as your propagation delay. Okay, and even with this, like it's shown here, you could get negative delays. So negative delays in the sense, so let's say this was your input, right? So your input is transiting and your output is transiting. So output transits from, so let's say this is 0 to VDD, and you're going from VDD to 0 here. So when your input transits from VDD by 2, I mean from 0 to VDD, then your output transits from VDD to 0, And essentially you're saying that from the point where the input transits VDD by 2 to the point where the output is crossing VDD by 2, that's my propagation delay. But sometimes it could be negative in the sense before your input reaches VDD by 2, your output is actually crossed VDD by 2. And that's possible because let's say you have a big driver like this inverter, and you have a tiny inverter driving this, then this input is very slow. But let's say, so what are we showing? High to low. So this is going low to high. Sorry, this is going high to low. This input is going low to high. Output is going to high to low, right? So high to low means this Nmos is basically on. And so as soon as this input becomes, so this is your inverter here, this input becomes higher than the VT of this device, if this is really large, because this is a large inverter, it'll start pulling down the output. So let's say the load also was very small, it'll start pulling down the output. So your output might transit faster than your input, so you might get a negative propagation delay. But we'll assume that, our gates are sized such a way. So this is a very non-optimal sizing, obviously, but we'll assume that the gates are sized such a way that this doesn't occur. Okay, so that's what um, we are going to call our propagation delay. So when your input is going high to low, we'll call it TPHL, and when your input is going high to low, we're going to call it, I think it's the other way around. I think it's the output when it goes high to low, then we call it TPHL, and when the output goes low to high, we call it TPLH. Okay, so this is inverter. Just quickly to show you, what the expression for a inverter is. And in an inverter, if you assume that your input is actually transiting infinitely fast, in the sense that you go from 0 to 1 instantly. So then, for example, so you can see this is for TPLH, so low to high. So low to high means your Pmos is charging. So you started with the output 0, and this Pmos is charging your output to high. Um, and because you are assuming that your input is infinitely going from high to low, then this Nmos is completely off here. So it's pretty much only the Pmos charging this capacitor, right? And if this current is, let's say we call this ILH, then, and the load capacitance is CL, then, if you write the equation for your current through the capacitor, it's CL dV over dt. And if this was a constant current, then delta V is equal to I times, or let's, delta T is equal to CL times delta V over I, right? And in this case, we'll call that I as ILH. And since we are measuring from VDD to VDD by 2, this delta V is going to be VDD by 2. So that's CL VDD by 2 over the charging current, right? And so this will be your TP. So this is a propagation delay from output going from low to high, right? So you're charging the output capacitor. So you can similarly write TPHL, high to low, is this one here, where you're going from VDD by 2 to ground. And that is again going to be, if you apply the same principle, it'll be VDD by 2, and the current is going to be IHL, which is the Nmos current here, right? So this is the Pmos current, this is the Nmos current, right? Nmos current. Okay, so now what is this current? So let's take an example. Is this linear, saturation, or both? So let's take an example. So I'll take the example. So by the way, throughout this lecture, I'm going to stick to the book pretty closely. So this is chapter 6 in the Hodges book. So you all can go back and refer that chapter, if you have some doubt, you can obviously ask right now, but I would definitely suggest, because I'll be, skipping a bunch of stuff. I won't go in detail through everything. I'll just give you the principle behind, most of these delay calculations and optimizations and so on. So, so let's take an example in the 0.13, which is from the table in the book. So in the 0.13 microcontroller in the book, VDD is equal to 1.2 volts. VT is 0.4. So when it's VT, that means VTN is 0.4, VTP is minus 0.4. And ECL, yeah, that is for I think this is for Nmos. Yeah, I think this is for Nmos. ECL equals to 0.6 volts, right? So you remember yesterday we derived the VD-SAT equation with the short channel effect with the velocity saturation. And that equation was the modified equation, which was VGS minus VT times ECL, and VGS minus VT plus ECL, right? So this was basically the correction term to our old VDSAT, which is VGS minus VT. And if you plug the equations here, 1.2 minus 0.4 is 0.8 times 0.6 divided by 0.8 plus 0.6 is 1.4. And this is obviously volts. So that is approximately equal to 0.34 volts. Okay. So which means that as long as, and yeah, this is for NMOS. So as long as your drain voltage is higher than 0.3 volts, then you're in saturation. So obviously when it goes to 0.3 volts, below that it is in linear, but from 0.6 to 0.3, 0.6 to 0.3, it's going to be in saturation. So we'll assume that most of the time it is actually the current is saturation current. So it is little optimistic, but that just makes your life easier to calculate it. Okay. So your TPHL is going to be CL times 0.5 VDD divided by the ID sat of N. So this is, like I said, it's approximately equal to that, just to make your hand calculation easier. Obviously, when you do it in SPICE, you're going to get a more accurate number, but this is good for SPICE. And now this is mostly in saturation, but it is easier for us to write it in effective resistance. So, typically when we are doing delays, we want to model this as a RC, right? So we want to model this as some effective RN times CL, right? CL. And if you remember from the equations, VDD times C to the power minus T over tau, and this tau is RNCL. If you want to reach from VDD by 2 to 0, or from 0 to VDD by 2, reach 50%, that's usually equal to 0.7 RNCL, right? So this is your TPHL or TPLH, and this, if I equate it to 0.5 VDD over ID sat N, then the CL will cancel, and then I can write RN is approximately equal to 0.5 VDD 0.5 VDD over 0.7 times ID sat N. Okay. And for a unit length transistor, if I calculate this, Then for any other transistor, I can just calculate it as Rn times L over Ln over Wn, right? So that way, once I calculate it for the unit transistor, I can just keep scaling it with L over W, because when I scale it over L over W, this ID sat also scales with that L over W. This VDD remains the same, CL remains the same, and then your time constant, essentially your effective time constant, will also scale with your L and W. Okay, and typically L is minimum, so we can uh, excuse me, we can just scale it with respect to W. Okay, and similarly you can write for RP, for the Pmos, it will be 0.5 VDD divided by 0.7 ID sat n, because you ID sat P, because if you do the same calculation for VD sat for P, you'll realize that most of the time it is in saturation region. So um, um, then you can effectively take the saturation current as the current throughout the charging period. And if you take it throughout the charging period, then then yeah, actually, I'm sorry. So I said most of the time. It's actually going to be all the time in saturation, because what we are saying is that we're not charging it all the way to VDD, or we are not discharging it all the way to the ground. We are discharging it from VDD or VOH to VDD by 2. In case of CMOS, it will be VDD to VDD by 2. And in case of this one, it will be from VOL to VDD by 2. In case of CMOS, it will be 0 to VDD by 2. So if it is 0 to VDD by 2 and your VD sat, for example, we calculated is 0.3 volts for the NMOS, then obviously for the entire discharging period from VDD to 50%, it's actually going to be in saturation. So I take it back. I was telling you that when we go to 0, but we don't go to 0. We are calculating only till 50% of the time. So it is actually pretty accurate, considering that the entire time it is in saturation region. Okay. All right. Let's quickly calculate an example, which is again given in the book. So we'll do for the same 0.13 micron technology, and we want to calculate the R equivalent for Nmos and R equivalent for Pmos for a unit size transistor. So unit size transistor means we are looking at W over L as zero point 0.1 by 0.1 micron. So the idea behind this is this is your minimum length, right? So this is L minimum in this particular book example, at least. I mean, in reality, if you're doing 130 nanometer, this will be 0.13, sometimes 0.1 as well. So because this is not a allowable W in most cases, but what we're trying to do is we're trying to figure out effective resistance for this, and then after that, in order to calculate the real resistance effective for a given W, let's say for a NMOS, then we just take R UQN and divide it by W, right? Because the L remains the 0.1. We're not changing L. So as we increase the W, the R effective goes down by the same amount. So excuse me. So I'll take the values from the table, which is provided in the book. So let's calculate ID sat for the NMOS first, ID sat. And if you remember the equation we showed yesterday is V sat times Cox VGS minus VTN square and divided by VGS minus VTN. So I can, so because this is digital switching, I don't have to write VGS because they're all VGS is equal to VDD. So I can just write VDD, and this is VDD minus VTN plus the critical electric field times the length of that one. Okay. Now, if you remember yesterday, I did some rearrangement, and I said I can write it also in the format where it is mu naught Cox over 2 W over L, and VDD minus VT square. This was our old equation. And then the correction term is EC and LN times the ratio of the low field mobility divided by the high field mobility. And these are process parameters which are given in the table. So I'll just plug those values. VTN square plus the electric field length over here. So I like writing it this way because then it gives you, what is this correction term here compared to your old value. In fact, what you can do is you can calculate this value and keep it for a W over L of 1, and then every time you just add this correction factor. So it kind of gives you an idea on how bad is the high field factor. So if I plug in all the values from the table, this actually turns out to be 276 microamp. So this quantity here turns out to be 275 microamps, and then ECNL is given as 0.6 volts for Nmos. Mu naught over mu effective for 0.13 is about 0.5 for Nmos, and divided by 1.4, which is this square plus ECN is 1.4 volt. So that's approximately equal to 59 microamps. So you can see that because of the high field, I mean, your reduction from our old long channel approximation, it's a huge reduction in the current, okay? And which means that the R effective is also going to reduce by the same, or the R equivalent N is going to reduce by the same amount, which is VDD 0.5 times 1.2 volts divided by 0.7 times ID sat N, so which is 59 microamps. And this is roughly equal to, if I calculate it, excuse me, it's about 14.5 kilo ohms, okay, 14.5 kilo ohms. And you can see that if we had used the long channel approximation, this would have been 276 divided by 59 times 14.5. If I calculate that, so 14.5 times 276 divided by 59, sorry, 59. So, sorry, that was around 59 divided by 276. So this should have been actually, so R, I'll call it long channel. If you calculate it with your old equation, it would have actually been 3K, okay? And that's huge because this is almost 5x lower, which means that if you had calculated a certain delay, you would be 5x off, okay? So, again, like I said, you can still use it to do like very close approximations, but using this will get you a little bit more accurate, actually quite a bit accurate. So that's why when you go to short channels, you'll see that the effect is huge, okay? So, and you can do the same thing for the Pmos. So I'll just write the equations directly. And for Pmos, our equivalent P is going to be 92 microamps. So this is your sort of your old long channel ID set times the correction term, which is 2.4. This is ECL. And for Pmos, mu naught over mu effective is about 0.39. This is all from the table at the back of your textbook. This is where I'm getting all the values from, 3.2. And this is roughly 27 microamps. And again, you can see it's almost a 3x reduction. And here you can see that the reduction in Pmos is actually less because if you remember when we did the velocity saturation, we saw that it is the velocity saturation happens earlier for Nmos. So you actually get a benefit, the ratio benefit, which used to be like almost 4x. So every time you want to keep the delay same, you want the Pmos to be 4x larger. But because of this velocity saturation, it's more like 2x larger. Okay. So, and if you plug in this into the REQP, it's 0.6 divided by 0.7 times 27 microamps, and that's roughly 33 kilo ohms, right? So in other words, you can write this as, you can write this RE so you can write this as REQ N is 14.5 kilo ohm per square, right? Because this is like sheet resistance now, and then REQP is like 33 kilo ohms per square. So if you have a certain W over L for the Nmos, it is going to be this equivalent value you've calculated over L over W for the Nmos, and for the Pmos will be REQP, the equivalent L over W, just like the way you calculated the resistances for wire models, right? It's the same here because it's the same phenomenon basically. Okay, so this is just to give you an idea on what kind, how you're calculating effective resistance. So although it's actually a current source, you kind of approximate it to what would it look if you actually had a resistor there, because we want to calculate it in terms of taus instead of carrying I over C's all over the place. So it's just easier to do calculations. Any questions so far? Okay. So it's all RC. So we calculated R, and then we are going to look at the intrinsic capacitance of the MOS model. So I thought I'll just revisit what we. So I'll just quickly go through it, like in 4 or 5 minutes. The slides we went through during the MOS MOS lecture to show you what the individual caps are. So for example, you can see here. This is, for example, let's say this was an NMOS here. So this is your poly, your gate, and let's say this is your source, this is your drain, right? So the caps you have, and if you remember, we have two types of caps, right? One is the oxide cap, and other is what we call the junction cap, the PN junction cap, basically. So all this, the C overlap is this extension of the poly onto the source and drain. So that's your the overlap caps here. So they're usually much smaller than obviously the gate cap, and the gate cap, which is from poly to the channel, and that is bias dependent, like as we showed last time. I'll show the slides again. And for the source and drain, these are actually reverse bias diodes. You remember we did a pretty detailed derivation of this cap, and this is dependent on the area and the sidewall. So I've shown, for example, sort of the 3D version of this junction here, source and drain junction, and the cap is given by the bottom plate times the area of this bottom plate, and then the perimeter times the sidewall cap, because they are different coefficients for it. So usually in the process model, you'll find different coefficients for it. It's a little bit more complicated than this, but in principle, it's the same. Okay. And from the layout, if I show you what the different caps are, so I already told you that two types of caps. You have the oxide caps, and then you have the junction caps, which are the diodes, basically, all the depletion caps. And if you take the 4-terminal transistors, so your CGS is basically the gate oxide cap, which contains the gate to source. And if you look at the layout, it's essentially this red portion here. And then the CGD portion is from that middle to this thing, but it depends on your bias, like I'm going to show in the next slide. And for the source to bulk are the junction caps shown in green here, and they're to do with the source and drain area. And so that's your drain to bulk cap. So these are essentially your 4 main caps. And then you have the overlap caps also. So when you're cut off, your CGS and CGL is just your overlap caps, and you always have the drain caps no matter which region of operation you are in. And your gate to bulk looks like the series cap, which is the oxide cap plus the depletion cap in series. So it's a very small cap. So you can see in the cutoff region, your CGS is 0, CGD is 0 here, and then the gate to bulk cap is the CGB, which kind of, as the depletion starts increasing, this cap starts decreasing, and once the inversion is formed, then that cap is 0 because you have a channel formed here. Okay, so in linear region, the caps are split half-half. So you have half COX CG on the gate to drain side, and you have the other half from gate to drain side. This is just the way they're partitioned because you have 2 nodes. And then obviously you have the overlap cap always there, doesn't matter which region of operation, and you have the drain to bulk as well when you're done. And in saturation, from gate to drain, you just have the overlap cap. The gate to source, you have 2/3 of the CG, which is the oxide cap, and you have the drain cap as well. Okay, this is saturation. When we are going to do the delay calculation right now, what we are going to assume is the worst case. So we are always going to take CG is equal to W times L times COX. Okay, this is what we're going to assume in our derivation so far. This is just to show you what the caps are and how they vary, but we'll just take the worst case values for these caps. Okay, and then for interconnect, so in these derivations, I'm not going to include, or the both for the logical effort and for path delay, we're not going to consider the interconnect because that is layout dependent. So that is actually done sort of post design. So this delay optimization and all that is done pre-layout. So you don't have this information, but I just wanted to show that this is also part of the delays. Okay. And we talked about the interconnect, and something was talked detail about the different models we use. So every wire is basically RC, and you have the lateral caps and then the bottom plate caps, which is the area plus the fringe caps, especially with the shorter nodes, because they're so close by that the fringe field is much more important right now. This is kind of a diagram showing you what are the different types of caps when you have all these wirings going on, and then the different types of models you use to approximate this wire delay caps. And this is basically showing you, if you have gates and this nets, how the parasitic extractions are done and annotated, and how they'll look eventually depending on which model of um, interconnect model you have chosen. Okay, for the load capacitance, so let's say this is the gate I'm interested in, and I want to capture the CL. So this CL, if you just see from this diagram, it is CL is equal to the C self, which is, I'll show you in the next slide, which is basically the self capacitance of this gate, and then C wire, which I just showed you in the last slide. And the C fan out is basically all the gate capacitance of all the gates you're driving from these inverters. So C fan out is basically all these caps over here is captured in this C fan out. Okay, so that's your sort of your total cap. And if I calculate the C fan out, like as I said, if this C fan out, so we are not going to take this C wire. We're going to look at the C fan out and C self now, because this, like I said, is actually layout dependent. So I cannot predict before the layout, but this and this one actually we can predict before the layout. So C fan out is basically the summation of all the gate capacitances, right? And if you look at each of the gate capacitances, so I've kind of um, expanded one of these inverters like gates over here. So like as I showed just in previous, couple of slides, so you have for the gate, you have the overlap caps, right? You have the two overlap caps, and you have the gate ground cap, which is basically taking the CGD and CGS and clubbing them together. And like as I said, we are for this purpose, we are going to take the worst case, which is W times L times Cox. That's your CG. So in other words, I can write CG is equal to that's the total gate capacitance of this. Excuse me. The total gate capacitance is CGN plus 2 times the overlap cap plus CGP plus 2 times the C overlap cap. So basically, these two caps are C 2 times COL. This is CGN. So that's your, yeah, this should be P. This should be N. So you have CGP plus these two overlap caps. Then you have CGN plus these two overlap caps. To be more accurate, this actually is not COL. This is 2COL because of what's called Miller effect. I'll explain that. I have a slide explaining what Miller effect is. But this is how it's derived in the book, so I'll just leave it that way. This is a very small portion, so it's not a huge error. So I'll just leave it that way. Okay. And if you calculate CGN, uh, like as I said, CGN, we are going to say it's Cox times the L, which is minimum L basically, times WN plus COL times WN. And we write COL basically because this is given in, usually femtofarad per micrometer, right? Because the overlap cap is fixed. The extension of the overlap cap, if you look here, okay, here, for example, if you look here, this is that LD, right? LD here. So that's a process parameter. So that's once you get it from the process, that's known, whatever it is, 1 nanometer, 2 nanometer, 3 nanometer. It'll slightly change over process from slow, fast corner and all that, but it should be pretty close to that. So typically, so then as you're increasing W, it just scales with W. So that's why this is 2COL times the WN. And then CGP is same thing. It's COX times, so this is LN. So we are just going to keep L to say that it is minimum L. And then WP times 2COL times WP. Okay. And COLN and COP are usually the same. So we just denote it as COL. They slightly differ, but not a whole lot. Okay, and I can write this as COX times L plus 2COL times WN plus WP. Okay, so this is your total gate cap, right, for one gate. And if you have n gates, then this would be summation of n gates, so it will be n times CG if you had n of these, right, n fan out. Okay, so everyone follows this. Any questions on how we calculated this? Essentially, we are just taking all the parasitic and the intrinsic cap and adding them together as a function of W and L and the COX parameter as well. And if you see your textbook, actually for 0.13, I'll just give you the numbers. You can calculate this. You'll see that CG, you can calculate it as 2 femtofarad per micrometer, and that'll be almost the same for CGP as well. I mean, P and N are the same. Okay, so if you have a certain W, then the total cap CG is going to be W times this small CG, which is, so if you have a 1 micrometer cap, 1 micrometer width, then it's going to be 2 femtofarad. If you have 2 micrometer width, it's going to be 4 femtofarad and so on. Okay. So this, this quantity here is what I've written as 2 femtofarad per micrometer, because you have Cox times L here, and this is actually per micrometer anyways. So this is femtofarad per micrometer. So depending on what your Wn and Wp is, you multiply that to get the absolute value of your um, capacitance. Okay. And similarly, for other gates, like if you have a NAND gate, this is going to be so, 2 femtofarad times the WP1 plus WN1 plus your second gate will be whatever WP2 plus WN2 and so on, right? So you just keep adding them. So let's say, you had one gate here with WP, W1, L1, WP1, WN1, and this was WP2, WN2, and this was WP3 and WN3. Then you've already calculated for this technology 2 femtofarad. You just keep adding all the W's and multiply it with 2 femtofarad. Okay. All right. Any questions? Okay. Like I said, you just go through uh, the book, because there are a lot of other examples and information. I'm just kind of showing you just the meat of it so that you at least understand the basic principles of it. Okay, so the self capacitance for this gate, so I've shown you this gate here, and basically showing you the self capacitance. And the self capacitance is whatever is the capacitance of your own gate hanging at the output. Okay, so obviously this drain to bulk capacitance is shorted, so that is not in the picture. This is also not in the picture, and all the gate source and gate to source cap here, they're actually at the input, so that's not in the picture as well. So these two are gone as well. So all you have is the overlap cap from, the drain to bulk cap from here to VDD, and then the overlap cap from here to the input, and same thing for the Nmos, right? So you can write now the C self is equal to the sum of these 4 capacitors, right? So it's CDBP, CDBN plus COL, but this is actually 2 COL times 2 COL because of what's called Miller effect. Okay, and I'll explain that in the next slide. Because what happens is, this is a digital gate. Every time this goes from low to high or high to low, this is obviously going high to low. Or if this was going low to high, that means your input is going high to low, right? So they're always in the opposite direction by the same amount VDD. So it looks like, so if you have a capacitor, and this is always, this is going one direction delta V, and this going in the other direction minus delta V, then you can make this look like a capacitor from the same node to ground as 2C, okay, because of the Miller effect. So just take it for granted now. In the next slide, I'll explain it. Why is that the case? So, so the junction cap, um, so the junction cap is CJ junction times WN. And here in the textbook, obviously it's taking all the sidewall and the front as one. So it's just taking the perimeters out, but if you have to be accurate, then take the perimeters as well, because the bottom walls are actually the most dominant ones. Okay. So yeah, I should write this as small COL. So this is basically per unit length. So femtofarad or per unit length per micrometer, right? And then you multiply the W plus WN just like before to get the total cap. And just like before, you can take the CJP, CJN, and COL as one effective cap times WP plus WN, assuming that CJN is equal to CJP, which a lot of times they are very close. So if you calculate that for example, for 0.13, this is roughly about 1 femtofarad per micrometer. Okay. So for example, let's say now you have an inverter where WP is equal to 2 micrometer and WN is equal to 1 micrometer. Then the C self is going to be 1 femtofarad times 2 plus 1, 3 micrometers. So 3 femtofarad is going to be your C self. Okay. All right. So before start for question, I'll just explain the Miller effect. So the Miller effect, like as I said, if you have, so let's say you're trying to find out the value of the cap for this with respect to ground, right? Because I'm always doing it with some reference node because this node is swinging. So if I have to find out for the reference node, now in a gate, like especially in a digital gate, like an inverter, whenever this is going high to low, this is going, low to high, this goes high to low and the opposite, right? So because of that, this can be approximated, this capacitor can be approximated as two capacitor, one capacitor from input to ground, a value of 2 COL, whatever was this overlap cap, 2 times of that, and one cap from output to ground as 2 COL. Okay. And like as I said, if you have a capacitor, some value C, and let's say you actually before I do that, so let's say you have a capacitor C to ground, and then you increase this voltage by delta V, right? And this is C, then Q is equal to CV, right? C times delta V. Or in other words, C is equal to Q times delta V here, right? Now, if I increase it by delta V, and this end is actually switching by minus delta V, then my Q is twice right now. So if Q is twice, then I can write C is equal to delta V by Q, but my Q is now twice because although on my side, I just increase it by delta V, the other side actually went down by delta V. So the total charge here instead of Q, there is going to be 2Q and minus 2Q here. And if I equate this with the previous cap, so let's say this is my new cap, C dash, or let's call it C Miller, CM. Then if I equate it with the previous cap, sorry, this is 2Q by delta V. So if I equate it with my previous cap, this was originally my C. You can see here, so I can write this as 2C. Okay, so that's what's called the Miller effect. So the Miller effect is actually so in analog, for example, we have this effect a lot, and it's more general in nature, where it says that if you actually have a gain element and you have a capacitor here, for example, this is your C, then this you can equate it to or actually this is minus A, this is minus A, then this you can equate it to a equivalent circuit where you have this minus A, you have one cap which is C times 1 plus A, and the output is C. Okay, so it's kind of similar here, but it is kind of a simplified effect here where the gain is just 2 all the time, okay, or, gain is -1. Okay, so that's how, in your previous example, you got 2 COL here. 2 COL here is because of this. And that's why I said in this example, this should have also been 2 COL, right? When I wrote this equation over here, I wrote 2 COL, but that 2 COL is just adding this COL and this COL, but it should have been COL plus 2 COL because this is swinging, this other node is swinging on the opposite direction. But, I just, in your textbook, it is 2 COL. So I'll just keep it that way because it's not a huge error. So we'll just keep it that way. Okay, any questions on what we have covered so far? It's either making sense or no sense, I guess. Just like I've been saying even yesterday, these are some of the kind of the additional effects and topics from what you have learned so far in basics. So try to get the gist and the principle of it. That's more important than getting into the details of it. So I'm obviously going to the details of it to kind of explain it to you, what the textbook is going. I mean, you can read the chapter, but this will hopefully help you go through it faster and maybe understand it a little better. But, if you're having trouble going through exact steps, like I said, just try to understand the principle behind it. So that way, at least next time, like, for example, if you become a digital designer and, so let's say you become a STA engineer. I mean, that's the first thing your boss is going to ask you is like, do some delay path analysis using logical effort, and hopefully this will come back. But it's not going to come back if you're not going to do it on your own. So I strongly suggest go back and at least do the examples which are there in the book, which I'm also kind of following here as well. And that'll make it stay for a lot longer. Once you do it on your own, then most of it will actually stay pretty much forever with you if you do it on your own. Otherwise, they'll just disappear. I mean, they'll disappear within an hour. At least that's what happens to me. Okay. All right. So if you remember, I mean, there was a lot of information on the first few days when Puneet was taking the course. You remember he introduced some timing models in the .lib, and he said that the delay is not only dependent on the load cap and the resistance of your switch, but it's also dependent on your input rise time, right? So the .libs, which I'll try to go through one of the example ones on Friday, is a function not only of the output capacitance, but it's also a function of your input rise time. And so in these next 2 slides, I'm sort of going to show you in principle why that's the case, and show you graphically. So I think this is a great diagram in your book, which sort of gives you a very nice intuitive feeling on why that's the case. But there are some derivations also, how to derive like some crude approximations of input rise time dependent. I'm not going to go through that. It's you can go through the book. So like I said, I'll just explain you the principle, and you can pretty much go through it. So in our previous examples, we have taken this, right? And which means that we are assuming that the input completely switches to VDD or ground. So either the PMOS is completely on and the NMOS is completely off. So you have IPMOS, which is just ID sat flowing into the cap or out to the cap using the NMOS, right? But in reality, this slope is going to be, a finite rise time. And when it is finite rise time, then you have during the transition period, both your NMOS and PMOS active. So instead of this I out, so initially we calculated I out is equal to CL dV out over dt. And this I out, we just said it is IP MOS for charging or I Nmos for discharging. But if you have a finite rise time at the input, it's really I Nmos minus IP MOS for part of the times the output, right? So for part of the time, like for example, for the charging time, it will be this for a little while, and then once the PMOS shuts off, then it'll be all IPMOS and so on, right? So this diagram kind of explains in a nice way with this color diagram over here. Um, so so what it shows you is that as you're traversing, so this is Vin, right? The x-axis is Vin, this is V out, right? So when your input is 0, output is VDD, then obviously there is no current flowing, there is no I out, right? And when your input is VDD and your output is 0, that means it is settled, obviously, then there is no current either, right? So you have I out 0 in both the cases, right? So this is the two settled case. Now, the case we have been calculating so far are actually these two ends here, right? We have been calculating these two ends because we assume that we switch the input from 0 to VDD immediately. So we kind of go lightning fast to this node. And then we use this current to calculate, which is basically, in this case, it is IN-MOS, right? Or the other way around, where we say the input is VDD and it immediately goes to 0. And that means you have your PMOS fully on, and this I out is equal to IPMOS, that ID set of PMOS, right? But if it is going somewhere in between, and also if you see this curve here, that's actually your VTC, right? So if you're traversing this, also your I out is always equal to 0. In other words, if your input is like really slow, right? Then your output is going to follow this curve, right? So your output is going to kind of follow this curve. And then obviously your delay will be, depending on whatever this is, your delay will be just, you can derive the delay straight from the VTC curve, right? But if you are having this ever changing, slow changing input, then your charging and discharging current are going to be either side of this curve, basically. Okay, so that's what this is showing you. So in the next slide, actually, it's shown what I've been explaining so far. So you can see that, for example, in our fall time case, so you give your input a step like this, and then if you see this diagram, basically this is what you're following, right? You go boom, your input, and then your output is kind of just following this path, where so and goes to 0. It goes from I max to 0. And because we assumed that like when we are doing TPLH, right, and TPHL calculation, we are actually calculating the delay from here to here, and we said the current is almost constant, which is in this case ID sat n, right? So for this whole time, it is ID sat n. But if you have a finite transit time, then depending on how slow it is, so if you're a little bit slow, then you're not going to get till here because your output would have started going up. So you're kind of following this curve right now, right? So your current is not I out max, it is lower than I out max. If it is even slower, then you're following this curve, which is even slower. And then if it is further slower, then you're following this, which is even slower. And then ultimately, if you're really slow, you're just following this, which will be whatever it is, your VTC, and that will be the slowest. So that's why it is dependent on our input rise time. So this is a little bit of a complicated calculation. So people actually characterize this straight from SPICE, and they actually feed this as as a function of your rise time straight into the .lib file. And when we go into the .lib file, we'll see how they're fed into that. So that way, when the when in digital where they're doing synthesis, they can actually go through this lib file and then do a synthesis and then find out, oh, this path is actually too bad. Maybe I shouldn't synthesize it this way. They'll go back. The algorithm basically will kind of retract back and sort of try to synthesize it in a different way to make the delay faster. But that's how they calculate the delays. Basically, the table actually has for different rise times. So obviously you have to have some granularity. So with certain granularity, they'll say, okay, if the rise time is going from 1 picosecond to 100 picosecond, they might have 10 tables, and they usually call it what's called the timing arcs. And depending on these inputs, the delay will vary. And the tool knows that, because the tool knows that for a certain load, what the delay of the output is going to be. So that will be the input of the next stage, and they will calculate it from that .lib file and so on. Okay. Makes sense, everyone?
Yes, sir.
Okay,
Yes, sir.
good. Okay, Ashwini, you're saying unable to grasp everything at this pace. Okay, what are you unable to grasp? What is the fundamental question, Ashwini? Do you have like a specific question, or you just like having trouble with the whole thing?
So actually, it's a bit fast, so I'm unable to get anything, everything.
Okay, then I'll suggest just, what I'll suggest is first actually go through the book. Okay, try to get it, then go through the video, and
Yes,
that you just have to kind of go back and forth, right? Because if you have a specific doubt, then obviously I can cover it. But if you're saying, just right from the beginning, then it's difficult to do that. Okay.
yes,
Yeah, but just like I said, understand the principle of what we are doing. We're trying to basically model the delays, because that's essentially what you're going to do in digital design. In digital design, if you're back-end designer, like in STA, static time analysis or something like that, all you're doing is you're doing delay analysis all the time. So that's why you need to have a clear understanding where the delays are coming from, right? So essentially they're coming from your resistance of your switches, your load capacitances, your delay of your input rise times. These are the three things we have discussed. And basically what I'm showing is, so for example, delay of the switches, the delay comes from the resistance of the switches. So I sort of showed you what is the switch resistance dependent on. And we said, if you're doing 50%, then it is dependent on just the ID sat current. Okay. And then we looked at the cap. What are the caps, different caps? So the fan out cap, which is the gate cap of all the gates, we calculated all the different types of caps, which you have already covered, and how to sum it up. And we took a technology and we said, okay, typically it is the length is always minimum. So you calculate per unit wide for unit length cap, so which we calculate, like for example 2 femtofarad per micrometer, the CG. And from there on, whatever is the size of your WP, WN, you just keep multiplying and adding them together, and that's your total capacitance, right? So that was your capacitance. And then I showed you now that the output delay is not only dependent on the R and the C. So basically not only this effective Rs. So this is your RP and Rn, and the CL, which we showed, that is C self plus C wire. We are not considering C wire right now because those are post layout. And the C fan out, which is the CG of all the gates which connected to. Um, but it is also dependent on the input rise time. And that's what I'm trying to explain here, why it is dependent on the input rise time. Because if your input is really, really slow, this I out, which we considered ID sat, it is going to be lower than that. It is not. So what we have been considering is I max. But if you have a finite rise time, then it is going to be less than that. How much less? It's a little bit complicated, right? So that's why I'm showing you graphically to give you a feel that why it is slower. But so that's why when people characterize it, they actually characterize, they do spice simulation with every possible rise time. And then they take that data and put it in the .lib file. So that way, when the digital synthesis is going on, it is only looking at a small file of few bytes, not like megabytes of doing calculations of KCL, KVL of all nodes, because it doesn't need to do that now, because we have created a nice model. And that's the model we are kind of developing here right now. Okay. All right. Hopefully, like as I said, hopefully it makes overall sense. Some of the details, if I'm going fast, like as I said, these are kind of, sort of advanced. I shouldn't say advanced topics. It's still like if you're getting interviewed, people will still ask you about fan outs and delays and everything. So it's not like, this is like a M-Tech topic. This is still a B-Tech topic. But for this course, scope of this course is a little bit advanced because people spend an entire semester going through this. I mean, we're spending a lot of time, but still we have to skim through some of the stuff. And that's why I said, when you're watching these lectures, you take as minimal notes, but you just pay attention to what I'm saying, just get the gist of it, and then you can go back to the videos and the book. So I've been posting on the GitHub page, all the section numbers and everything. So you can just go back and read it. So like yesterday also, I followed the book very closely, and I have given you all the section numbers on the GitHub page. So you can go back, and then if you go back immediately and just follow it, and you say, oh, okay, this is what was happening. If you go back after, months, years, or even few weeks, then it'll be all again foreign to you. All right, so now, like as I said, we're going to, before I try to explain you how to optimize certain path in a complex digital circuit, one of the things we use independently, and this is also going to sort of help you understand the optimizing, is how to optimize a delay for a buffer driving a large load, right? So for example, okay, let's take an example. So we calculated, let me see, what did we calculate? Okay, so we did, if you remember, we did an earlier example where we calculated R equivalent of N is 14. So I'll just take it approximately 15 kilo ohm per square. And then REP is, I'll just take approximately 30 kilo ohm per square, right? So let's say I had, so this is for 0.1. So let's say my W was 1 micron, and that's 10 squares, right? Because 1 by 0.1 is 10 squares. So then Rn for that inverter would be 15.5, 15 kilo ohms divided by 10 is 1.5 kilo ohms. So let's say let's say this inverter had a size of 2 micron by 0.1 micron. That's your P size. So this is your WP over LP, and the N is, let's say, 1 by 0.1, right? So we had calculated that for per square, it is 15 kilo ohm per square. So 1 by 10 is 10 squares. So I divided by 10 because the resistance is going to reduce because it's L over W, right? So you're going to get effective resistance, which is 1.5 kilo ohms for the N, right? So this is Rn, this is Rn, and Rp is going to be 20 squares. So 30 kilo ohms divided by 20 squares is also 1.5 kilo ohms, right? So that Rp is, so both of them on. So that's how I chose the W over L's hopefully. Now let's say I want to drive a large cap. So when I say large cap, let's take example 500 femtofarad, right? So I want to drive a 500 femtofarad cap. So what's my TP, LH, and TP, HL? Okay, this is a problem for you guys to solve now. I mean, it should be very easy. So solve and tell me what are those numbers? So like I said, we have taken all that IDC-SAT and everything, and we just made into a RC. So it's just very simple to calculate, right? So what should be TP, LH, and TPHL? So what's the rising time propagation delay and falling time propagation delay? So remember, TP, LH is, you're assuming you give a input high to low infinitely fast, let's say. So finite, right? So it goes high to low. Sorry, TP-LH is low to high. Yeah, TP-LH is low to high. So you give an input really low to high. That means your Pmos is sitting at ground. So VGS is VDD, and it is charging this 500 femtofarad cap. And I want to know from low to high. So from 0 to VDD by 2, what time am I going to take? And this one, like I said, Rn, we have calculated to be 1.5K. Come on, this should be like 5 seconds. I should be getting answers, like my chat box should be blinking right now. Okay, TPLH, one answer is 512 picosecond. What about others? Come on. So people understand this problem, or I mean, you're completely lost? Okay, TPHL, TPLH are the same. All right, how about the rest? Alok, what's your answer?
Doing so.
How about the rest? Vratiranjan, Shruti. Sumant, what's your answer? Okay, take a few minutes. Okay, Shruti, 517. About you, Shumant, you're still solving? Okay, 518. All right, so at least few people. Hopefully, rest of you are at least getting what the problem is. So because we have approximated this to a R and C, so essentially it's just a RC, right? And I'm asking you what time does it take to reach VDD by 2? And this is 1.5K, and this is 500 femtofarad, right? So for a RC, a simple RC, just have some of the ballpark numbers with you, right? So when you're doing TPLH, TPHL 50% to 50%, so or in other words, when you're looking at from VDD to 50% or 0 to VDD by 2, then that's 0.7, right? You remember we didn't derive this one, but when we did the circuit theory, we derived for tau, we derived for 2.2 tau and so on, right? And 5 tau. But for 50 to 50%, if you do the same equation, it is 0.7 times RC, right? Or 0.7 times tau. This is tau, right? Okay, so a lot of people are getting the answer now, which is good. So, which means that TPLH is 0.7 times, and and because it's K is 10 to the power 3, and femto is minus 15, so this is 10 to the power minus 12, which is picosecond, right? So I can just write 1.5 times 500 picosecond, right? Instead of carrying the 10 to the power 15 and 12 around. So get used to doing calculations like that. When you're doing IC design, you'll be always dealing with kilo ohms and femtofarads and picofarads. So you just write like cancel the term, so that way it'll be easier. So if you calculate this is what is it? So if I do 0.7 times 1 point times 500, that's 525. Okay. So some of you got 517, some of you got, maybe you guys took, I don't know what you took, but you got 517.5. Maybe 707 or something you took, I don't know, but it's close. I think you guys got the idea. So this is TPLH. Now, TPHL is the same because RP is also 1.75K. So your high to low, that is your Nmos pulling it low, is also going to be the same. So TPHL is also going to be 525 picosecond. So the propagation delay, which I forgot to show you, usually it is shown as low to high, high to low divided by 2. In this case, since both of them are same, so the propagation delay is also 525 picosecond, right? Which in a fast technology, this is very slow because you should be operating at, let's say, picoseconds. So how do I make it faster? What do I do to make it faster? So I cannot change. So this is RC, right? RNCL or RPCL. I cannot change C. So the only thing I can change is R, right? So let's say now I want to make it twice as fast. So I want to make TPHL equals to TPLH to be, let's say I want to make it half. So 250 plus 12, roughly 265 picosecond. Okay. I want to make this. How should I size the inverter to make that quickly? So my WP and WL are this size right now, right? So this size is giving me 520 picosecond. What should I change the size to 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 give me a faster delay? If I want to make it half, let's say I want to go from 525 to 265, which is half. What should be my sizes now? Double the length? No. Remember, your Rp or Rn is equal to the R equivalent times L over W. Okay, you increase L, your resistance is going to increase. You increase W, your resistance is going to decrease. So what do you want to do? If you want to reduce the, yes, Suman, double the W, right? Not double the L. Because you want to reduce this by half, you can't do anything for C, right? So you have to basically increase the W by twice, right? So for example, WP will become 4 micron, WN will become 1 micron. That'll give you 250. Let's say I want to go further down by another half. I want to make it 125 now. I mean, what is this? 250 is uh, 125, roughly 125, let's say. I want to make it half of that. Then you want to again double it, right? You want to go 8 and you want to make this 2, right? And if I want to go even further lower, then this will be 16, this will be 4, right? So I can do that. So that's what I'm trying to show here. So let's say I want, so what is this? 265, this gives you roughly, so let's say I want to go 50 nanosecond. So I have to make 10 times. So I want to go 52.5 nanosecond. I want to increase this by 10 times, right? So let's say I wanted TP to be 52.5 nanosecond, right? So then I need this buffer to be, this big buffer to be, WP should be 10 times 2, which should be 20 micron by 0.1 micron. That is WP LP, and the N should be 10 micron by 1 micron, 0.1, right? If I do that, then this delay is going to be 52.5 nanosecond, right? So this is what I can do. But what's the problem now? The problem is somebody is driving this guy, right? Somebody is driving this guy. Suddenly now the gate capacitor has increased 10 times, right? So this CG, CG new now is 10 times CG old, which means that this gate which was driving here is going to be 10 times slower now, right? So that's why, so which means that, okay, so I increase the size, then you can say, okay, maybe I'll take another buffer and make it a little larger. Then you'll say, okay, something is driving this. What should I do this? You'll say, okay, I'll make this larger. Then so you just keep going like this, right? And that's why this whole problem of optimization comes to. So when you have a big load, you can't just take one inverter and size it up, because that's not the optimum. So now the question is, okay, I can do multiple stages. And so first stage will be the biggest one driving the main load. Second one would be a little bigger and driving the gate of that. So basically this is your 500 femto, and you say, okay, I'll take the 20 by 0.1 and 10 by 0.1 and drive this. And now I say, okay, this is slow now. So, okay, I'll size this to, let's say the P will be 10 now, and N will be 5. I say, okay, this has to be driven. So you'll say something like this, right? But you're just like guessing now, right? So so that's what we're going to look at now, how to come to a sort of a closed form solution to see if there is a way where we know what the optimum is. Can we do some math and find out what the optimum is? And that's what we're going to do in the next couple of minutes. So what we want to look at is, so we are purely going to look at inverters right now. So if you have an inverter chain, how are we going to optimize the delay for a given load and given fan in voltage, or C in basically? So this is your C in, and you have certain C out. How are you going to optimize? How many stages are you going to have, and how are you going to optimize it? And then we'll basically apply that same principle to arbitrary arbitrary gates. Okay. So what we are going to do is we are going to kind of formalize this in a way which will make our derivation a little easier. So let's first calculate C in of a inverter. So let's say I have an inverter with some arbitrary size. What is the C in? What is this gate? So C in, I can write this as CG. Remember, this CG is this, uh, like some capacitance over length, right? Because we are saying that the length is always minimum. So we are not going to change the minimum, because you never, in digital circuit, you never want to change the minimum length, because you want the fastest device, right? The fastest device is for the minimum length. So you don't want to change that. You just want to play around with W's. So this will be Wn plus Wp, and we ignore the overlap cap and all that for now, because this is the majority of the cap. So to keep it simple, we'll just ignore that. And this I can write it as Wn plus 2 times Wp, because you remember when we did the VD stat calculation yesterday, we said that with the new saturation voltage and the Pmos is going to be twice as slow as the Nmos. So to keep the delay same, then you want to keep the, sorry, this is Wn. You want to keep the size of the P twice the size of N. So that'll keep the uh, delay same. So this I can write this as 3 CG times 3 times Wn, correct? So that's your C input cap. Now, for the N, R effective N, we have already calculated it. So your effective Nmos is going to be the equivalent resistance we calculated times L over W, right? And if you have calculated the equivalent as for, let's say, minimum length, then you basically take R equivalent over Wn, because you've already calculated for the minimum length. So if I want to calculate the what's called the self delay of the inverter, or the inverter's delay, so tau inverter, I want to see how much, what is the delay for this equivalent R and C in, not C out, because I want to see that when I'm increasing my sizes, right? As I'm increasing my sizes, how am I increasing my input? So how am I able to drive my input capacitor? Because like, as I said in the previous example, you're trying to drive the output by increasing the size of the WP and WN, but you're increasing the input as well. So we're going to write the tau in as R effective C in, and this will be a little bit more clear when we derive it. So just bear with me for now. So this is R equivalent ln WN, times CG times 3 times WN, right? And so WN cancel. So I can write this as R equivalent times CG times 3 times ln. So this I can write it as the sort of the self delay of the inverter, right? And this is interesting because, like, as I said, this actually captures the input cap when you are increasing the driving capacity of the inverter, right? So this is a good way to formulate it, because you just can't keep increasing your drive because you're increasing the load cap. So this basically tells you sort of the self delay. What is the self delay of this load? And we can use this in the formulation coming. Now the delay for the rise time and fall time, if I write the delay for this rise time and fall time for the output, then this is going to be T delay is going to be R effective, either P or Q, and we're trying to keep all of them same. So uh, C self, right? C self is nothing but your parasitic capacitor of the for the Mos, right? So all the CDB and all that we calculated in the previous slide. That's what constitutes C self. And C out, you remember, this is a C wire plus all the gate capacitance of the next load, right? So if you have all these gates in the next stage, so all their gate capacitances are calculated in C out. Okay, so that's your delay. And I can write this delay in a format which will make it obvious why we wrote this expression here. So if I take multiply by C in and divide it by C in, so I'll take R effective times C in and divide it by C in. So this will become C out over C in plus C self by C in. Okay. So now you can see this is nothing but the inverter self gain, right? So I can write this as tau inverter over C out over C in plus in the textbook, I call it the gamma inverter. This is nothing but your parasitic cap ratio, basically, parasitic cap ratio. So essentially C self to C in is what the ratio, okay? And there's a quick example. If you see the book in example 6.8, they calculate for again for 0.13, tau inverter, that is this R effective times C in, which we said 3 times R equivalent times CG times LN. And this, if you calculate, it's using the table values again, it's about 7.5 picosecond. Okay, so that's like the self delay. This kind of gives you also a good idea of the speed of this technology. So if you know an inverter is 7.5 and you want to drive it like in gigahertz, you know that it's going to be pretty much impossible to do it because you just driving your own gate cap, it's a delay of 7.5 picoseconds. So you can't do better than that. Okay, and then gamma for that technology is C self by C in, and if you calculate this using the values in the table, it's 1 femtofarad per micrometer by 2 femtofarad per micrometer, which is about 0.5. Some numbers to just kind of give you an idea, you know, what it does look like. Okay. All right, so now what we're going to do is we basically say, okay, like as I said, so we set some. So just remember specifically this equation here, which we are saying the delay of an inverter driving your load is the self delay tau inverter times the ratio of the output cap versus the input cap, which you're going to call out as the fan out, and then this parasitic cap ratio. Okay. So now we are saying we have a large load, you know, like we give an example, and we start with a small driver with the input cap of C in, and we're going to add a series of these inverters. So what we are trying to find out is two things: how many number of stages, and what's the fan out. And fan out is basically how big is this size compared to this, right? Because we start with a like I was saying, we start with a big size and then we go smaller and smaller and smaller. So what is this ratio, right? And that'll, so we want to know how many number of stages and what should be the ratio between the sizes of these two stages to give me the minimum delay for a given C in to C load. Okay, and that is the best you can do for that technology. Basically, that's what we're trying to derive here. Okay, so for this, I can write the total delay as oh, before I go to the next slide, any questions on this? How we got the self delay of the inverter and the delay of the output. Delay of the output is obviously what we have been doing so far. Just take the R equivalent times C out. But the delay of the inverter, like as I said, it's a quantity we just defined to kind of give us an idea how fast a inverter can be in this particular technology. And like as I said, it'll be more apparent in the next derivation here. But if you have any questions, just stop me. Okay. So the total delay is basically the sum of all the inverters, from um, 1 to n. Let's say I have n inverters. And you remember this, we calculated it as the output load by the input load and the parasitic ratio of that inverter, right? So for a given J, this is going to be whatever, 20 by 10 or whatever it is, or 5 by 2 and so on. So they are scaling. So this is kind of how we write it. And we want to minimize this, right? So this is the delay we want to basically minimize it. And you can go through the book, but basically what it is you so what if you look at the book, what it has done is you'll see that it has taken 2 stages, because it knows that they're all probably going to be symmetric, because there's nothing in this formulation which tells you that it is not. If that's the case, it tries to minimize this 2 delay. So it says, okay, what if I take the 2 inverters somewhere in between? So it's going to be tau inverter times the CJ times CG times WJ plus 1, that's the output cap. So let's say I've taken this 2 inverters here, right? So basically it's CG times, this is the output is CG times the WJ plus 1 of this inverter, which is the total W, P times WN, and then CG times this inverter, CG times WJ. This is what we wrote in the last equation, right, in the last slide. So I'm just writing this in this formulation, then give inverter. And then I do that for this one here, which is plus tau inverter sorry, I can do either way. So yeah, so let me just keep it that way. So I'll do, in your book, it's actually J and J minus 1, but it's fine. You'll understand. So this will be CG time J plus 1 plus gamma. So basically, if I can minimize this, then I apply the same principle for all the other stages, and that should probably hold true. So in other words, I want to minimize this delay. I take the partial with respect to WJ. So I'm trying to find out what's the WJ such that this delay is minimized, right? So I take the partial of this and make it to 0. So what will it be? And one of the interesting results which comes out is that, not therefore, one of the interesting result which comes out is that you find out that WJ, that some jth inverters WJ, which is basically WP plus WN for the jth inverter, is equal to the geometric mean of the inverter in front of it and in the W of the inverter behind it. Okay. So this is what you'll get if you followed this derivation. And one way to do this is size the inverters in this fashion. So if I take one and F times the next one and F squared times the next one and so on, you'll see that, let's take the example of this, right? So F is equal to F squared times 1 root over, so that's F, right? If you take, like, for example, this one here, then Fn minus 2 is equal to root of Fn minus 1 times Fn minus 3, which will be this again, and so on, right? So that's which will be F basically. So all of them just turn out to be F. So if I have a fan out ratio of F and I just keep multiplying F by F, then I'll meet this delay requirement to minimize the delay requirement. Okay, so it still has an answer. So what it means is that the C load is basically F to the power N C in, right? Because this load is F times Cn. This load is F squared times Cn. So if I keep doing that, then this load is equal to F to the power n Cn, right? That just from our definition, the way we have formulated this problem, it just comes from that. So now the question is, what is n and what is f, right? We still haven't answered that question. So what that previous derivation gave us is that if you size it in such a way, in this geometric fashion, you'll get a minimum delay, but it still hasn't answered us like what is this n and what is this f, right? So the n I can find from this equation here, right? So I can write n from this equation is the natural log of C load over C in. So this ratio here, which is the ratio of this load versus this, right? Divided by the natural log of the fan out F. So in other words, if I know C load, if I know C in, which usually I know, then I can find n, but I still need to know f, but I don't know f, right? I need to find that f. So we need to find another equation which will give us hopefully this, or at least graphically this. So we find, so for a gate delay, in this case, an inverter delay, we know that it is the self delay of the inverter and Cj, that is the cap of the driving and the input cap of itself and this parasitic cap, right? That's your gate delay. So then I can write the total delay. Total delay I can write as, because it's n stages, so I can write it as n times tau inverter and Cj over Cj minus 1. So it's still not a closed form solution, but it's just formulating it in this fashion, right? So this is the total delay. And this is nothing but F, right? Because the ratio of this cap to this cap is F, this cap to this cap is F, this cap to this cap is F, because that's how we've done it. So I can write this as equal to n times, which we've derived it as ln of, I'm just going to write C load as CL times Cn over natural log of F, and then times tau inverter, and this ratio is F and F plus gamma inverter. Okay, so that's your total delay, right? It still hasn't given me a closed form solution for it, which is, you can see it's difficult to get a closed form solution, because if I take, so let's say this is D, right? So what I want is, I want tau D over tau F set to 0, right? That'll give me, but it actually has two unknowns here, CL, Cin, and then gamma inverter. I don't know what the gamma inverter is. If I make gamma inverter equal to 0, then you can do this and get it. But what I'll show you is a graph here. So this graph is actually plotting this equation here as a function of F. Function of F and gamma. So for different values of gamma, so for example, this is gamma 0, which means there is no parasitic cap, which is obviously unrealistic. And this is, and we just calculated for 0.13, gamma is 0.5, right? So which is this curve here. So this curve here is gamma 0.5. And if your parasitic is even higher, then this is for gamma equals to 2.2. And from this curve, you can see that the delay, the optimum delay. So this is the minimum delay. You can see this is where, for this curve, this is the minimum delay. This is the minimum delay here, and so on. So it's somewhere around. So this is 3. So somewhere around maybe 2.5 to 4. Okay. And if you do this tau d of tau f equals to 0 for gamma equals to 0, you'll actually find out that f is equal to e exponential, which is what is e to the power I think
2.693.
yeah, 2.693. Thanks. 2.69. So if you didn't have any parasitics, it'll be, but this is obviously unrealistic. So for gamma, you can see it'll be close to 3 or maybe 4. So a lot of times, at least, when I design buffers, I have to design a buffer. Usually I just take 3 stages and fan out of 3, n equals to 3. And I know it's not optimum, but it's very close. And if you're not trying to squeeze everything out of the technology, then you're usually pretty good. Okay. So like I said, if your gamma equals to 0, then the theoretical value shows that's E, which is about 2.6. And but like I said, a lot of people for gamma greater than 0, they actually use 3 stages. N equals to uh, 3 for a fan out of 4 here. You can see it's 1, 4, 4 times 4, 16, and so on. Okay, so this will approximately give you very close to the minimum delay. Okay, did this make sense, or any like some very basic question is like, what's going on here? Don't understand this or that. So essentially what we did was, if you remember, we said we want to drive this large cap. We just can't take one inverter and size it, because when you do that, that inverter's gate cap, somebody has to drive it. That gets slower. Then you say, okay, I want to beef up that inverter. But if you do that, then the one previously that becomes slower. So then we said, okay, looks like we need a series of inverters and we want to taper them. And we want to find out how to taper it. Before we did that, we kind of formulated this sort of the self-inverter delay, which is basically this R equivalent times this C in, right? Which is not what is charging, but it is a good metric to show how fast is this inverter in this particular technology. Not only that, we actually use it in our uh, in the next derivation. So we use that tau inverter, the delay of the inverter, and formulated the delay this guy will take to charge the C out and its own parasitic cap in terms of this tau inverter, which we calculated as this, right? Which is basically the self delay times the output cap divided by the input cap plus whatever is the parasitic cap C self divided by the input cap. Okay, so that's the total delay. And we said, okay, now let's take the series of inverters and try to figure out how we want to scale it and how many number of stages, right? So we did this and we said, okay, let's take 2 of these stages and try to minimize it, because every other 2 stages is probably going to be symmetric. And we took that and we found out that the size of for this stage is going to be the geometric mean of the size of this times the size of this. In other words, size of this times size of this, square root of that is the size of this. And then we said, okay, one way to do that is we just scale them by square terms, right? So if it is a geometric mean, then we do the square terms so that every stage is the geometric mean of this divided by, geometric mean of this size times this size, what you get, right? And we said, okay, if that's the case, we calculated the total delay as a function of tau inverter and the fan out. And that gave us a fan out, and that gave us this graph, which basically showed us that it depends on your parasitic. If your parasitic is large, your fan out is going to be large. If parasitic is small or 0, then your fan out should be roughly around 3. So you can take that fan out and plug it in this, given your C load and C in, and that fan out, and that'll give you the number of stages you need. And that's why I said, typically we use 3 stages with this, which gives you, roughly the same number. Okay, 2.7, that's fine. It's close to 2.7. So, makes sense, everyone? Any questions on what we have done so far? So basically, we are going to use this method to now sort of find arbitrary paths and how to minimize that delay. Okay, so let's do an example now. This is an example by the book. And so the first question is, so let me give you the parameters. So C load. So this is the load capacitor is 200 femtofarad, and C in, which is basically the minimum size inverter, I guess, is 1 femtofarad. And it's asking you to compute the fan out ratio, compute fan out if n is equal to 3. So I want 3 stages, and if n equals to 3, what should be my fan out ratio? Okay, so do this calculation first, and then we'll. So I'll give you the equation, the relation between n and fan out. So this is ln is equal to natural log of CL over C. Okay, so use this expression and tell me what the fan out should be. So fan out is basically what is the size differences between the first inverter, second to third, and so on. Okay, someone says 2.3. Okay, so just use the expression. It's pretty straightforward. Use the expression, values are given to you. And so basically the question is, that's the load to C in ratio. And they're telling you that the problem basically tells you that it is a stage of 3. So you have 3 inverters basically. 3 inverters in this fashion. So this is 200, and this is the input cap for this inverter is 1. So this is obviously your first inverter with size 1. So this is F. This will be F square, obviously, right? So whatever this size is, WP plus WN, the size of this inverter will be F times WP plus WN. This will be F square WP plus WN. Okay, so I'm getting 2.3, 5.84, 5.8. Okay, so let me just quickly calculate and see what should it be. So like I said, you just apply this expression, and so here if I write ln of F is equal to ln of CL over C in, which is 200 divided by N, which is given 3, right? So then F is equal to e to the power ln of 200 by 3. And if I calculate that, it's 5.84. Okay, or roughly let's say 6. So in other words, if you are given 3 stages, so if your boss tells you no, don't use more than 3 stages, it's going to cost you, just minimize the delay with the 3 stages, then you use this equation and this will give you the minimum. So let's say this size was 2 micron WP and 1 micron WN, then this will be 6 times, so this will be 12 and 6, and this inverter will be 12 times 6, which is 72 micron and 36 micron, right? So you can see that if I just took a 72 by 36, it's not going to work because this tiny guy will have a huge delay. So you actually taper it down. So you take 12 by 6 and then you do that, right? Everyone got this, right? Okay. Now the second part of the problem is, but this is not the optimal fan out, right? So we have seen that the optimal fan out is around 2.6. So if we remove that restriction of 3 stages, so it's basically asking you, so it's given you 2 more data. It's given you a data of tau in equals to 7.5 picosecond, which we calculated if you remember before, and gamma equals to 0.5. This is also we calculated, right? So with this, now yeah, so with this now you find out what is the optimal fan out. Sorry, so what's the question here? If you want to improve the delay, we first remove the restriction of the number, compare the number of stages to solve current. Okay, so what is basically saying is that take the F from the previous graph. You remember we for gamma equals to 0.5, we're going to take somewhere around 3 plus. So it's actually given you that the minimum is actually at 3.6. So basically it's saying that for gamma equals to 0.5 in the previous graph, we saw that the fan out should be 3.6. Now with these values, now calculate N. What is N? Use the same equation and calculate N. So tell me what the N is. Okay, 4.14, 4.12. Okay, good. So yeah, pretty straightforward, right? So now the F is given to you, so you find out N. So N is equal to ln of 200 over ln of 3.6, and that's roughly 4 point whatever, 4.1 or 4.18 or whatever. But obviously I can't have fractional stages, so I need to take the nearest decimal. So I'll do 4 stages, right? So 4 stages. Now, Yeah, 4.3, 4.2. Okay, so 4, like I said, and I can't have fractional stages, 4 stages. Now let's calculate the delay with 3 stages with fan out of, what did we calculate the fan out? 6, right? Roughly 6. And now with 3.6, the 4 stages. So let's calculate the first one. Okay. So now let's take the total delay of the first one. So total delay of the first one is, if you remember, it's n times tau self inverter times Cj over Cj minus 1. Yeah, so which is, sorry, this you can just write it as fan out, right? So it's basically any stage to any stage ratio, but they're all the same, which is the fan out ratio. So this is equal, so let's calculate the first one. So the first one was given to us 3 stages. Tau inverter is 7.5 picosecond, and the fan out for the first one was 5.84. And if you do this calculation, you'll get approximately 143 picosecond, right? So that was the first one. Now let's see, after we optimized it, how much different is it? So total delay of the optimized one is, now it's 4 stages and 7.5 picosecond, and the fan out now is 3.6, right? Or 3. Yeah, 3.6. Actually, it was, so the problem had given 3.8 by mistake. I wrote 3.6, but that's okay. It's close enough. And this is equal to, so this is 4 times 7.5 times 4.1.
123.
Yeah, 123. Thank you. 123 picosecond. So you can see, I mean, it's 20 picosecond difference, but you know, a lot of times, if you're, like as I said, if you're not trying to squeeze everything out of it, I would actually go with the 3 stages, right? Because 3 stages is simpler to design, less time to lay out and all that. And just the difference is about only 20 picosecond. Okay. But if you want to really squeeze everything out of it, then find the minimum F from the given gamma, use that fan out to find out the number of stages. And that will be close to this thing, right? And if you didn't do this buffer sizing, right, if you just use this minimum buffer over here, then the delay is going to be tau inverter 1 stage, that is tau inverter, and this is 200 over 1 plus 0.5 I can ignore, so this tau 100, so it is going to be 200, so that is what, 100, 700, 1400, 1.4 nanosecond, right? 1400 picosecond, right? So you, by doing this staging of the buffers, you made it 10 times faster, right? Which is huge. Okay, everyone clear what we did here? So essentially we just took an example trying to see. So this is something you do a lot in design actually. So just remember, so like I said, when I'm designing, usually I don't bother calculating. I just do 3x or 4x fan out, put 3 stages and I'm done, because I know it'll be like few picoseconds off here and there, because you can see, right? If you go from 1 stage to 3 stage, even with your non-optimum one, you get 10x improvement, and that's good enough for me. Then after that, it is just squeezing everything out of it. So if I'm not, like I said, if I'm just designing a buffer to get just the maximum benefit out of it, I'll just do 3 stages, do 4x or 3x, and I know it's going to be pretty close to the minimum one. Okay. Any questions? All right. Now what we're going to do is, so what we have been doing so far, we have been setting the stage to sort of do optimization, not in just buffer chains, but arbitrary paths, right? So for example, like I showed you in the first slide, that if you're like, for example, a STA designer, right? And you finish synthesis and post layout, and or just after synthesis, you get your timing result, and you find out that there is a critical path which is avoiding you. So that it says that this is the critical path. So critical path means this path here. Any low to high or high to low is traversing this path and finally coming out here as a low to high and high to low. This propagation delay is actually restricting you from operating at full clock speed. So like I said, if your clock speed was 100 picosecond for, let's say, that is what, 10 megahertz, and then this delay path, let's say, turned out to be 120 picosecond, then you're going to fail your timing. So a lot of times people, they say, okay, this is in one corner, I won't be operating in this corner that much, it's high temperature, I'm going to slow the clock speed, I'm just going to go with this and I'm okay. But most of the time you have to go and fix it, and a lot of times it's just not in one place, it's like multiple places, right? So that's why it's good to sort of know how you can optimize these paths. And so we are going to use the same. So now what I'm going to do is I'm going to just introduce you to the concepts, and because there's a lot of material in the book, it's just one session, it's going to be difficult. But not only that, it just will get like really detailed, and you guys are already um, kind of falling falling off the cliff. So what I'm going to do is I'm going to just introduce the same concept now that I've developed the material for it. I'll just introduce you to the concept, and then um, you'll know what. So next time when somebody asks you, okay, what's the logical effect in this path, at least you know the principle behind it, and you can go back to the material to know it. Okay. So here we apply the same sort of principle. So if I want to know the total delay in this path, so let's say this is the total delay of the NAND gates, then just like I did at the inverter, I sum all the NAND gates, and I can do the same principle like I did the self delay of the um, inverter. I can do the self delay of the NAND gate and do the same output cap over input cap times the self capacitance of the NAND gate, right? So this is the total delay. I can write it in the same fashion, right? The only difference here is that this tau NAND is actually tau NAND worst, right? It's the worst delay, because if you remember when you're doing gates, the NAND gate is, you have two NOR gates in parallel and two in series, right? So for example, this is always going to be, whatever 2W, WP over 2. So whatever WP, WN, sorry, WN, WN. So it's going to be WN over 2, the equivalent resistance times the C load. But this one, depending on if the two inputs are transiting or one of them are transiting, it will be slower or faster. So, but we take the worst one, and the worst one is when one of this. So let's say this was WP, which is equal to 2 times, actually in this case, yeah, it'll be just WN, I guess. If that's the case, then this will be WP RWP times CL, which is the worst case delay, right? So that'll be the delay here. And then CJ and CJ plus 1 and CJ is obviously fixed, because for a NAND gate, depending on the sizes, this will be fixed. And actually, I should probably show you the typical sizes to keep the delay constant for the NAND gates. Actually, I'll come to that. Let me come to that. Let me just finish this. Okay, and the same thing, if you had a series of NOR gates, you would write it in the same fashion. Total delay of a NOR gate path would be summation of all the tau NORs Cj plus 1 over Cj plus the parasitic cap ratio of the NOR gate, right? So that will be the delay. And but if you have arbitrary paths, and so let me write the tau NAND for, so this will be R effective C in, just like before. And the NAND gate I'm taking here is so this is, I think, 2WN. Just give me a second here. So if you want to equate the delays of an inverter, so if for the inverter we had 2W and W, right? Because we're saying Pmos is twice as slow. So this will equate it, right? For a NAND gate, you had the two Pmoses, right? And you have two series ones. This is your gate and this is your output. So for the NAND gate, to equate it to this, then this is going to be 2W, 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 2W. To make it same as the inverter delay, then we're going to do this sizing, right? So then RFC in, I can write this as, and C in is going to be, so we'll have that R equivalent, just like we calculated before for the unit size, and ln over wn, because we're trying to keep both the L and P same, so we can take either one of them. And then the total cap, so total cap for each node, right? So if you take the AND gate, so each node is 2W plus 2W, so that will be 4W n, or because everything is a reference to n, times the CG, which is per unit length, right? So that's your total, that's your self delay of a NAND gate, which I can write as 4 R equivalent CG ln. And if you remember, for inverter, it was 3 R equivalent CG ln, right? So similarly for the NOR gate, so NOR gate sizing to get the same delay is going to be, sorry, this was NAND. Yeah, this was NAND. For NOR gate, you're going to get for, sorry, so W, so these are your PMOSes, right? And this is, let's say, A, and this is connected. This is your node B, and so sizes is going to be WW, because the inverter, in case of inverter, you have one W discharging the cap. So here you can see either this is discharging or this is discharging. So the worst case is, for worst case delay to be the same, I keep same as the inverter, WW. And for the PMOS to have the same size, then this needs to be 4W, 4W, because then the series is 2WP. I mean, and because PMOS is twice as slow, but you have two in series, so you have to put twice as big to get the series resistance same, and then twice more to get the mobility and the V saturation point low. So because it's the PMOS in series, now you get 4 times more. So NOR gate is now worse than the NAND gate because of that. So now let's calculate the NOR gate. So this is R effective C in, which is going to be R equivalent ln Wn just like before. And now the total cap, C in cap for one node is going to be 4 plus 5, 4 plus 1, which is going to be 5 Wn times Cg, right? So it is 5 times R equivalent CgL. So you can see that the inverter was 3 times. This is the NAND is a little bit worse, and NOR is actually worse than that. Okay. So we have the self delay for NAND gate, NOR gate. Now let's look at a arbitrary path, right? So you want to look at a arbitrary path which has NAND, NORs, and inverters. So for example, let's say, like as I said, you might, if you're a STA designer, you might get a report and it'll say, okay, this path is actually your critical path. So then your total delay in this path here, I can write this as is equal to the first one is a NAND, so I'll write it as NAND times Cj plus 1 over Cj plus the parasitic ratio of the NAND gate, and then plus the inverter, which is going to be tau inverter, and then the same thing, Cj plus 2 over Cj plus 1 plus gamma of the inverter, and then finally the NOR gate, which is tau of the NOR gate times the ratio of the output of the NOR gate, which is, we'll write it as Cj plus 3 over Cj plus 2 plus the parasitic cap ratio of the NOR gate. Okay, so that's the total delay. So if I can minimize this total delay, then that's the best I can do for this technology. Now, what is the minimum delay? Again, I will not go through the derivation, but the process is the same if you look at the book or look at some of the references. So essentially what the references do is like, okay, I have a series, let me just pull out just 2 of these, and if you pull out these 2 and you do the same thing, dj over d fan out d fan out equals to 0, you'll see that the result you get is tau NAND times the fan out of that that NAND gate should be equal to the inverter times the fan out of the inverter, J plus 1. Or in words, what you can do is you can put that you take any 2 stages, then tau times that fan out of that given stage should be equal to, that given stage should be equal to tau times fan out of the next stage. So in other words, if I take these 2, for example, I've already shown that tau of NAND times the fan out, which is this is Cj plus 1, right? Cj plus 1, and this is Cj. So basically tau inverter times Cj plus 1 divided by Cj plus the parasitic should be equal to, this is Cj plus 1, Cj plus 2, because this is the input cap of this stage, should be equal to tau inverter times Cj plus 2 divided by Cj plus 1 plus tau inverter, right? So in other words, these 2 quantities should be same. These 2 quantities should be equal. If I had next 2 quantities, they should be equal, and so on. So that's what basically the derivation comes out to be. So in other words, like I said in the word, you want to make the delay times the fan out. Let's neglect the parasitic for right now. You want to make the delay times the fan out equals to the next stage delay times the fan out. If you do that, then you'll get minimum delay in that path. Okay. So let's take an example. So we have again some kind of a similar example where I have, you can see I have a 2 femtofarad cap and the output is 200 femtofarad. Now the question is, how do I minimize the delay, right, in this path? The number of stages are given to me. How do I minimize the delay in this path? Okay. Now, because from what we derived last time, we want to make tau. So just ignore the parasitic for now. So that means I want tau NAND times Cj plus 1 over Cj equal to tau inverter times Cj plus 2 over Cj plus 1 should be equal to um, tau NOR times Cj plus 3 over Cj plus 2, right? Basically, this is what I want, like ignoring the parasitic, which for now, let's ignore it to keep it simple. And here, if obviously Cj is equal to 2 femtofarad and Cj plus 3, which is the last one, is equal to 200 femtofarad, right? So that's the okay. So how do I minimize the path? Now, because all these need to be same, I want to find out what this quantity needs to be. So all these NAND plus this should be some quantity. And that quantity, I can just take the geometric mean of all the delays, right? So I can take so this is equal to tau, I'll say min, let's say. So I want to see what is this tau min. And that tau min is, I can set it as the geometric mean of all the delays, just like we did for the inverter, Cj plus 1 over Cj times tau inverter times Cj plus 2 over Cj plus 1 times tau NOR of Cj plus 3 over Cj plus 2. But I can replace Cj with C in here and Cj plus 3 with C load here. I'll call it CL, which is this here, divided by Cj plus 2, right? And then obviously all the j plus 1 cancels, j plus 2 cancels here, and this equals to root of all the self delays times the ratio of CL over Cin, right? That is the tau mean I want to equate all these two. If I do that, then I know. And once I know this, then I can find the rest, right? Because I know tau NAND. For a given technology, I know tau NAND. So tau NAND times Cj plus 1 over Cj, which is Cin, should be equal to this quantity tau min, which means that Cj plus 1 should be equal to tau min, which I just calculated, times Cn divided by tau NAND, right? So this will give me the value of Cj plus 1. Then I know the fan out ratio between first fan out ratio, which is Cj plus 1 divided by Cj. And I do the same thing for the other gates. Now, because these are not asymmetric gates, I can't do F square and all that. That was true with inverters because they were all the same, right? They were no. But now I have different types of gates. So you have to kind of do it one by one for each one of them, right? Okay, everyone clear so far what we did? So essentially we wrote the delay equation just like how we have formulated before, and we're trying to just minimize it for a given path, and we're trying to figure out how to minimize it. So it's clear till here, right? Any questions so far? Okay. One thing I missed here is the cube root. This is actually cube root, not square root. It's got three is okay. So okay, now let's so the problem is okay, so just using the previous values we calculated, we are going to minimize this path. So let's calculate what the value is going to be. So I can find tau mean is equal to cube root of, because you remember the last one we said the delay of NAND is what? 4 times R equivalent CGLN, right? NOR was 5 times. Inverter was 3 times. So I'm going to just write 4 times 3 times 5 times. That's the NOR. And then 200 by 2, that's the ratio of C load to C in, times R. I'll just, because this is, so I'm going to get cube of R equivalent CG times ln. So I'll take the cube root of that. So it comes out of the cube root, and that's what I get. And if you calculate this, you should get something like 18.2 R equivalent CG ln, right? So now we just start from the NOR and we keep going backwards. So tau NOR we can calculate using these relationships here. So tau NOR is going to be times CL over CJ plus 2 is going to be equal to 5 R equivalent times CG ln. This is for the tau of NOR, and divided by times 200 femtofarad over CJ plus 2. So this should be equal to 18.2 times R equivalent CGLN, and which means that CJ plus 2, we know everything except CJ plus 2, so you can calculate that to be 55.50 farad. And similarly, you do that for inverter, you're going to see that CJ plus 1 is going to be 9.1 femtofarad, and C in is obviously 2 femtofarad. It's already given to you. So that gives you the fan out ratios right now, right? So from this, you can calculate the fan out ratios. So because CJ plus 2 is 55, and so CJ plus 2 is equal to 55 femtofarad. And what is the total cap of CJ? It is 5, right? So 5 WN is equal to 55. So 5 WN times CG. 5 WN times CG should be, remember, right? So for the NOR gate, this each one is 5 times the minimum WN. So I'm just using that. Times CGN should be equal to 55. And you remember this we had calculated before to be 2 femtofarad. So if I use that, 5 times 2, so implies WN is equal to 55 femtofarad. Not 55 femtofarad, it is 50. Okay, what's the unit here? 55 by 2 femtofarad per micrometer times 5. Oh yeah, because this is unitless, this is micrometer, so then WN is equal to 5.5 micrometer. Okay, so which means that for the NOR gate, you remember you're going to size this as 5. So which is going to be 22. And similarly, you can calculate for the inverter. You do the same thing for the inverter and the inverter WN, WP. So here WN is 5.5 and WP is 22, right, for the NOR gate. And similarly, you can calculate for the inverter, which the WP is going to be 3 and WN is going to be 1.5, using the same equation here and equating it to this. And for NAND, it's going to be WP equals to 0.5. And for NAND, WP, WN is equal, they're the same. So they'll be the same, 0.5 micrometer. Okay, so that's how you do sizing for a certain path, right? So you're given a certain path and you use the same similar method we did for the inverter sizing, and then you just go uh, um, calculate what your ratios are going to be, and from that ratio you start from one end and you go to the other end. And once you know the ratio, you know what your gate sizes are, I mean gate multiples are. From that you can find out the exact sizes of the gate to minimize the critical delay for this path. Okay, so so for example, this will give you a delay of total delay. If you calculate it, you can calculate the total delay, right? So total delay is this one here. Where is the total delay? Did I write the total delay? Yeah, so total delay TD is going to be tau NAND times, if you just take the ratio of Cj plus 1, Cj, so on, tau inverter, Cj plus 2 over Cj plus 1 and so on. And if this turns out to be, let's say, 100 picosecond, right? So that's the best you can do. Now, let's say you got a timing error and you get the critical path and this shows as like, 300 picosecond. Okay, shows as 300 picosecond. Then you know that, okay, there is some non-optimal path in it. So you can calculate this and say, okay, this inverter is not sized properly, or all three are not sized properly. So you can go in and size them. Now, in a typical automated process, you don't have access to it. You do what's called ECOs, but at least if you're doing it on your hand, or if you're doing ECOs, if there is a way to optimize it or not. Like for example, if uh, the timing report comes back and says, oh, it's 100 picosecond, and you do the critical path analysis, and through this, and you find out that yes, it is 100 picosecond, I can't do better than that, then you basically are stuck with the technology or the architecture. You have to change either one of them. Otherwise, you're not going to meet the timing or relax the clock. Okay. Any questions on this so far? I know it's it could be a lot of info right now, but like as I said, just kind of get an overall idea. The overall idea of what we have been trying to do is minimize basically a certain path, right? So you have a series of inverters. In the first case, we took a load and we want to drive it and minimize the load. So there we had the option to choose the number of stages and the sizes. So, and we figured out what's the minima for that. But now we are given a certain number of stages and we are required to find out the minimum delay in that. And for that, we use the same method basically to minimize the delay. Okay. And the takeaway from this is basically this expression here is that you want to make sure that whatever is your minimum inverter delay or your NAND gate delay or NOR delay times the fan out should be equal to the next inverter or NOR or NAND delay times its fan out. That's what you should take away from this. If you do this for every stage, then you minimize that path, and that's exactly what we did here. Okay, now I'm going to just introduce this. Well, like as I said, at least just know this as a concept. Um, you know, it is there are a lot of elements to the logical effort. Logical effort is basically what we have done so far, but it is just normalized to your fastest inverter. Okay. So for example, uh, everything, all the delays are going to be normalized to an inverter. So we've calculated, we calculated tau in inverter, for example, to be what? 3 times its equivalent resistance times uh, the unit length capacitance times the length, right? So this is for inverter, and we have been writing everything in terms of this, right? So, but what we're going to do is now we're going to divide everything by this and normalize it to this. In other words, we're going to define the logical effort of, let's say, inverter is the tau inverter by the same tau inverter. In the sense, the logical effort is 1. So we know that the inverter is the fastest gate we have. So we want to just write everything in terms of this fastest gate instead of writing in terms of um, you know, the delay paths basically. 1 second, sorry. So the logical effort, so we are going to define this logical effort as the inherent delay of a certain gate divided by the inherent gate of the fastest inverter, basically. So for the inverter itself, it is 1, like as you said. And for NOR gate, like logical effort for NOR gate, LE NOR gate would be tau of NOR divided by tau of in, and then LE, the logical effort for NAND would be equal to tau of NAND over tau of inverter, right? So if I take the previous example, you know, where we had the total delay is written as what? Delay is equal to tau NAND times Cj plus 1 over Cj plus gamma of NAND plus tau inverter times Cj plus 2 over Cj plus 1 plus the parasitic component plus the last one, which was a NOR times Cj plus 3, Cj plus 2 times the gamma of NOR, right? So now what we're going to do is we're going to write it in terms of logical effort. So we're going to divide the total delay by the tau of the inverter. So that's the logical effort. Now we'll call this as the total logical effort, or the logical effort of the entire path, or the delay of the entire path normalized to the inverter. So basically we are just going to do this, right? And we define this, right? This is by definition the logical effort for NAND, and this is obviously 1 because this is the inverter, and this is the logical effort for NOR, right? So if I write this now in the terms of logical effort, now this is equal to logical effort for NAND times the fan out of that stage, right? The first stage, basically, we'll write it as 1, that, and then the parasitic effort of the NAND, because it is also divided by tau inverter, plus logical effort of inverter, which is 1 times its fan out, plus P in it, basically P inv is nothing but gamma divided by tau inverter. So this is gamma NAND divided by gamma inverter. And then the last one is logical effort of NOR times fan out of the last stage plus P NOR, right? So this is, it basically wrote the exact same equation in terms of the logical effort. So in other words, it's summation of the logical effort times the fan out of that stage plus the parasitic cap. So that's your total delay in terms of fan outs, right? So now the question is, how do we write this um, in terms of our fan out? So now we have derived, like for example, we have derived that the tau of NAND is 4 times R equivalent. So tau NAND is equal to 4 times R equivalent CGLN. So then I can write LE NAND is equals to 4, right? Because it's 4 by 3, because it's 4 times RCGLN, 3 times RCGLN. So R equivalent CGLN, that's tau NAND, and inverter is R equivalent CGLN. So this cancels, so you get 4 by 3. And then LE of NOR is similarly 5 by 3, and the inverter is obviously 1. Okay. So this is in calculation. If you want to measure it, there are ways to actually measure it. So for example, if you have, there are 2 ways to measure it. So let's say you have an inverter, right? So you size this inverter, this is 2W, this is W, and you size this inverter. There are 2 ways to find the logical effort for gates. Like if you want to do it by simulation, or even by calculation, is you want to set the delay of the inverter, right? Um, um, so for example, let's take an example. So let's take an example of a NAND gate. So NAND gate would be, I'm going to just write the number. I'm just not going to write 2 any, So this is the NAND gate, right? So for NAND gate, we know that in order to keep the same delay, this is going to be 2, 2, 2, 2, right? So one way to find out is you set the gate, the transistor sizes, so that the delay of this guy for the same load, whatever load you have CL, you're going to drive the same load CL here, right? Is the same. Then the logical effort is basically the ratio of the input caps. So C input of NAND divided by C input of inverter. So for example, here you can see it's 2 plus 2 is 4, and then 2 plus 1 is 3 for the inverter, so 4 by 3. So similarly, you can do for the NOR and you'll get 5 by 3. So that's one method, right? One method. Second method is you just choose whatever size is, equal sizes. So for example, you choose such that the gate capacitances are the same, and then you take the inverse of the delays. Whatever delays you calculate or measure, you take the invert of that, and that will also give you the logical effort. So those are the 2 ways to find out the logical effort, right? So that's how you find out logical effort. So let me take quickly an example, the same example, and we'll just kind of try to go through that example. I think. So this is just what I explained right now. So like, for example, you can see in order to keep the delay same, this is how I size a NAND gate. This is how I size a NOR gate. So the LE of the inverter is obviously 1. For the NAND gate, this is obviously the NAND gate, and the logical effort for that is 2 plus the CG over here is 2 plus 2 times W, obviously, times CG. And and this one is 2 times 1 plus W times CG. So if I take the ratio of these two, it's going to be 4 over 3. Same thing here. It's going to be 4 plus 1 times CG times W. And if I take the ratio of that, then it's going to be 5/3. So it's basically just telling you, and this is the other method I told you. So here you basically choose the sizes same. So you can see the Pmos sizes and the Nmos sizes, they equal to the P plus N over here. Then you find out the delay and take the ratio of the delay, and you'll find out that this logical effort is also the same. Okay, so now let's take this example and do the same delay analysis we did now with this logical effort and see if it is simpler. Um, so if you remember, so this is the this is your Cn and this is your Cl, which is Cj plus 3 and Cj. This is Cl. Okay, so we need to find LEFO. We need to equalize this first. And so the total path, and we'll call it the total path effort, right? Which is the logical effort of NAND times logical effort of inverter times logical effort of the NOR times C load over C in. And this, if you add all, put all the values, so this will be 4/3. So 4/3 times 1 times 5/3 times 100, 200/2 is roughly equal to 220.2. Okay, this is logical effort, right? There is no unit to it. This is, so basically it's telling you that this is going to be 222 times more effort than your fastest invert, which, and so this is the total. And if you remember, we said for each path, logical effort times FO should be equal to the square root of this whole thing. So square root of 222, which is about 6. So then now I can write the delay of the whole thing. So the delay is equal to okay. So yeah. So the whole idea of normalizing this is basically now I can find out the delay, total delay, as this logical effort times the number of stages, right? Because I've already equated them. So number of stages is 3 here. So I can do 3 times 6 plus all the parasitic elements. So you know, you have P NAND plus P inverter plus P NOR. And so this is gamma inverter by tau inverter, which is the NAND is 1, and this is half, and this is 3/2. So if you add all that together, this is equal to 21, right? So this is the total delay effort. Okay, this should actually be called as the cube of it, total delay. So or this is the minimum path delay. So now I can find out the minimum path delay as equal to tau of inverter, which is we have calculated before as 7.5 times 21, which is equal to 157.5 picosecond. So that's your total delay, right? So total delays. So now instead of carrying all the delays by themselves, what you did was you calculated everything as a logical effort compared to an inverter, and then you just multiply that inverter with the number of stages times the total logical effort plus all the parasitic element. So that's the beauty of doing this, is that you basically find out what is the number of stages total logical effort, take the square root of that, which is roughly times 6. So your total delay is 3 times that plus all the parasitic elements you have. So if your parasitic element was 0, this should be 18, right? And then you multiply that with tau inverter, and then you get 156 picosecond. So it's easier to, you can see it's easier to calculate, but it's also easier to see if where you can make corrections. Because for example, if this logical effort turns out to be more than 6, so let's say this was 8 or this was 10, you know you can optimize this because your total effort should be per stage should be 6. Okay, 6 times tau picosecond, tau inverter. So that's the beauty of doing this in the logical effort path. And and once you have that, then just use uh, the same equation we did before, but you just write it in terms of logical effort now. So logical effort of the NOR gate times C load Cj plus 1 should be 6 now, because now it is in terms of logical effort. So and logical effort of NOR gate is 5/3, so Cj plus 1 is equal to 4/3 times 6 times 6 times C load. That is equal to roughly 55 femtofarad. And then you do the same thing for, sorry, this is 5/3. This is NOR gate. And then Cj, sorry, this is Cj plus 2. And then Cj plus 1 is going to be the inverter logical effort, which is 1. And then 55. This divided by the 6 is the logical stage. So that's 9.1 femtofarad. So you can see we got the same result we got using the absolute delays. Where is it? Did we calculate it anywhere? Yeah, so here actually. So it's the same result. You got it here, and then Cj is nothing but Cin, which is 2, obviously. Okay. Any questions? I know this may be very confusing, but essentially what we have done is, so remember how we started, right? We started saying that what is the delay of one stage? Then we said what is the delay of cascaded inverters? And then we said, okay, how are we going to minimize it? And then we said, okay, now what if there is a NAND inverter NOR, like inverter? We use the same principle to minimize it. And all we did was, in that equation, we normalized everything by the delay of the inverter, so that we are not carrying picoseconds everywhere. Instead, we are just carrying this delay effort, right? So instead of carrying 6 times 7, 30 seconds picoseconds everywhere, we're carrying this number everywhere. So it's easier to see, easier to calculate. And there are other methods in the logical effort which you can use to minimize paths and all that. And I would highly recommend to go through the chapter. And this is a graph in your book which kind of gives you a graphical view of what a logical effort means. So you can see that this is the x-axis is your fan out. So for example, if you have an inverter with a minimum size, that's a fan out of 1. Not minimum size, the output and your input cap is same. Then this will be the delay of your inverter, so which is normalized to 1. And then as you are increasing your fan out, your inverter is basically going linearly up. So that's what's called your effort. How much effort is your inverter taking to give you that delay? And the NAND gate is actually 2-input NAND gate is normalized to the inverter. So it's showing you that the slope is higher. And the 2-input NOR gate is actually showing you that it is even higher. And what you can see here is that this is for a, I don't know why it's set 2, but this is for a fan out of 1. You can see for a given fan out, your NAND gate is worse and NOR is even worse. And then as your fan out increases, that is, if you're driving more and more load, you can see that the NOR becomes even worse and worse compared to your NAND gate, right? So as your fan out increases, your NOR becomes worse and worse. So that's why in a design, if it is a speed sensitive design, you want to use a NAND gate instead of a NOR gate if that's, if it doesn't result in a extra path or extra delay, then that would give you an advantage over a NOR gate basically. Okay. All right, I think I'll stop here. Like as I said, lot of information. I mean, not lot of information, but